Hi there again. Let's continue with Paraview story. So now let's move to the second one. Okay, so this is a 2D case. Now it previously was 3D, but we have seen that post-processor is pretty much the same. But in this case, the interesting thing that I want to show you is just some unsteady post-processing. So just go up to your training material, just extract the case, and basically what we have is this case, the classical vortex sharing cylinder that we use a lot. Okay, we really love this case, and basically we have the flow, and we're going to see things now in motion. Okay, so it's relatively easy. Okay, we have done it previously in the tutorial, but now we're going to show you some new additional features. So let's start extract this. So vortex shedding, extracting. So what I want to show you also that we converted here the solution, the one from OpenFOAM, to another format. It's called the Exodus format. So here we have this whole OpenFOAM solution, but in this format that is compressed on just one single file. Instead, the output of OpenFOAM, you have all those folders. So it's pretty much the same, nothing changed, okay? And as you also see that we have 3 states there with what we were doing. So let's see what we have, okay? So we go into the vortex shedding, you extract everything, and now let me launch here. Let me use, for instance, Parafoam built-in. Okay, so you can use Parafoam built-in, or Paraview. Okay, pretty much nothing. Okay, well, okay, yes, something that here it doesn't work. Parafoam, okay, or Parafoam works, but remember we're not opening the file, the OpenFOAM file. So let's use Paraview. Okay. So it's just pure Paraview. Okay, you can use also Parafoam, but you just need to load everything. So Paraview, and let me load the state. So we have 3 states, and let me load the first one, state 1. So remember, in your case, you will need to choose the right location. Okay. So you will have these 2 prefit file. So in my case, it's okay, it's fine, but in your case, you will need to choose. So here, what I want to show you is that this is the file, the input format is different, but you see post-processing is pretty much the same. The only thing that will change here now, variables have different symbols here. Now the Exodus data converted now differently, but it's the same as you use inside. Probably symbols will be different. You also will need to extract blocks. See that you have the blocks here. So the same idea applies here. Okay, so if you want to extract from the specific blocks and everything, just select that. So if you haven't used the filter, annotate time filter, this will annotate the time. So as usual, you go here and you have it somewhere here, annotate time filter, you put it there, and you will have some options. Okay, so what I want to show you here is that also we can compute gradients. We have seen that. So again, just to remind you, you go here alphabetical, you can compute the gradients. This case gradient U, I want gradients, compute vorticity, Paraview, and we can compute with the one that we have in OpenFOAM. This case Q criterion, we don't compute it, and in 2D, you don't use it. It's better to use vorticity, Q criterion, just use it in 3D, and you have your other options. But what is interesting is that here we can also compute temporal statistics. So see that we have now in the pipeline browser, we have it here. So be careful that this option also can be time consuming, because you need to compute the temporal statistic. Again, you compute temporal statistics of whatever you have in your solution, what you save from OpenFOAM. Again, it's better to get those statistics from OpenFOAM, but for some reasons you don't compute it and you need to get it from your output. You can compute it like this. So see that now here, it gives you probably a little bit more than what you can get in Parafoam. So Parafoam you get average. Okay, but here you can get compute minimum, maximum, standard deviation. Okay, and then the product, the fluctuation, you can also compute it, but you need to get here a calculator. But here you get the basic descriptive statistics. Okay, so all those fields will be available here. Okay, so what is cool here, that see that now here the original fields that you have here. So the original solution, you will have vorticity, U, P, okay, and your shear stresses. As soon as you compute your statistic here, those fields, the primitive field, will disappear. Now here you will have only your descriptive statistic. Okay, so you get average here. Okay, So nothing changed, okay? So remember, you want to access your original field, go here. Here you will have only the statistic. And see here the gradient, it is applied just in the original field. If you want to apply gradient to temporal statistic, just add it here. So you will see like filter, gradient, filter, and you have it there. And temporal statistic, okay, you select this one, and then you compute the statistics of all the time solution that you have. Again, you go here, alphabetical, temporal statistics, somewhere here. Okay, so you have many options, so see that you have it there. So what is interesting, what I want to show you as well is that I go here, and here we're visualizing vorticity. Okay, let me change the range, or it also we haven't seen. So you change there from -2 to 2. Okay, if you press play, you have the vorticity field there. So one of the things or confusions again that when you run simulation, when do I stop? So we have seen that you can compute the forces, everything, and when they are already, they reach a periodic behavior, you can stop. But that is getting that quantitative value, the forces, but also you can do it from a qualitative point of view from your solution. So you can compute the average, and then when you see that the average is not changing anymore, you can stop. Okay, so you have your quantitative or qualitative value. So here you see that we're looking at the instantaneous value. So actually let's look better at velocity. Okay, so as you play, you see that the velocity at the beginning, okay, instead, then you have the onset of the instability, and you have the oscillations here. Okay, but it's difficult to judge if this is, you can stop the simulation, it's not changing anymore. So what you can do is compute statistics. So as you go here, now we see temporal statistics, and we compute the statistics. So here now we are filtering those fluctuations, and let's see what happens. You press play. This is the mean value of all the iterations accumulated. So your criterion now will be that if your solution is not changing anymore, you can say that you have reached a statistically steady state. Okay, be careful listen to this expression. It's statistically steady. Okay, you are computing your statistic, descriptive statistic, and specifically the mean value is not changing anymore. Okay, so see that you can say that this is pretty much very statistically steady. Okay, so this is how you can look at that. Okay, so this is another way to judge your convergence. Okay, you have all your statistics there. You will have also maximum value of your whole complete computation. Okay, you have the minimum value, and then you have the standard deviation of the field. Okay, so this was regarding the statistics. Okay, so let me click here. Okay, and okay, so see you have some extra options there. Okay, so advanced, so it's up to you to play around. So this was the first file that we opened, the first state file. So let's open a second one. So let me launch again Paraview, and second state, load state. Let me see what did I put here. So okay, so I know I'm in the right directory. Okay, this is nice. So now here we make the sense a little bit more complex. So what we have, again, we're visualizing. Now we're going to visualize just, I think we're going to use, I think there is an extract bar somewhere, or we're going to visualize here the field, and then we're going to compute temporal statistics, but see that we're plotting over a line in a pro location. Okay, the same stuff that you can do with OpenFont, you can do it also here. Okay, and then also you can visualize how the solution is changing in time. So look at that, this is time consuming. Okay, see that is opening the file, it's computing this temporal statistic that, as I mentioned, can be time consuming, then all these gradients for all time steps. So it takes some toll to do this one, some toll of computational resources. So let's wait a little bit, let's see what happens here. Okay, so we have all our post-processing and see what we have. So here we're looking at the solution and see that we're plotting a line, and I'm going to just plot whatever I want along this line. And also see that here I have a spreadsheet, and here I'm plotting the values at one specific pro. You see this sphere here. So we're probing here, and then I'm plotting the solution here, okay, we'll plot over a time. So see that as you press play, it's very cool, very nice, very animated. So this line here represents your current time state and how the solutions is advancing. So the colors that you see here, it is just the sampling that we're doing, velocity and pressure. So let's see how we do this. Okay, so this probably there are another new filters that you haven't seen. So let me close here and close here. So we start from this original view. Okay, so close here, close here. So annotate time filter. So this is your original field. You put it there. Then temporal statistics is you want your statistics. So again, see that I'm visualizing this one, and it is computing all the statistics. Okay, so it's a little bit, can be a little bit time consuming. Okay, so be careful. That will take some time. So we don't want to work with this one. See that here we compute gradients in the original field. Look at the tree. Okay, so whatever. And then now that we have here some information, okay, so we start to plot over a line. So you have it here. So as you do this one, you need just to give coordinate. You see here the line, probably this is the line. Okay, so give coordinate and then you plot in that line. Okay, so you know your domain, you know how to do it. So in this case, let me go here and see that this is the line that I'm putting here in this cut plane, in this part of the domain, in this case boundary patch. Okay, so now what we're doing is just plotting the solution in this line, and you will have that information available for post-processing. So how do we visualize this one? So now that you have the, if you do it from scratch, automatically you will have the window here that will open, but I will show you how to open that window also manually. So you create a new view here, and then you want to plot over a line, but we want a line chart view, this one. You select this one that we want to visualize this, and see that we can access, you click here, it's the valid view, let's move, and see that now you have all the fields. So see that valid view, and now selecting this one, you move here and you will have the options what you want to see. See that you have all those fields. And let's say that I want to see velocity, and see that you have here. So velocity magnitude, and probably let me see also vorticity magnitude. Okay, so see that you can press now play, and then it will start to move here, and see that it start to measure that velocity here, and you can see the wake, where is the wake going. Okay, so it's vorticity, velocity. You can also fix the axis here. So let me stop here. You have all the options here. So here is moving, adapting dynamically, but you will have all the options here. It's okay, the title of the axis, if you want to change the axis, swap axis, you have all the options here. So you can play around here, okay? So the color, the size, type of font, and everything, you have it there. Okay, so I'm not going to play with those, it's up to you. So let me plot those velocity here and see how cool here you start to see the wake. So okay, so yeah. So instead of visualizing here vorticity, let's see velocity, and we're looking at this. Now we're looking at magnitude, and see that what we have is this. What we're looking is this information that is passing through this line. You are capturing everything, and you clearly can see the wake and how the vortices are switching and changing now there. So any quantity that pass here, that you can access or select here, and then all the quantities that you have. Okay, so also remember to select there, and everything that you have compute here in this tree, you will get access. Okay, so you can do the same with the temporal statistics. Okay, so let me do it. So I go temporal statistics, let me close this one, and let me compute here this. Okay, and you give here coordinates. So let me put it 10 from -20, 20, and then let me put it in the front face or in the middle. It's up to you. So here they see that you have that line, and here you have all the information passing through that line. Okay, so specifically now I would like to do the mean velocity. Okay, remember that that is applied to statistics. So you go here, you average, and you have it there. So let me go to the beginning and see that you have everything. So here we have the total average. Okay, So this is not computing instantaneous value. Also, we can get it how it's accumulated. So let me see. You will have an option here also to see all that accumulate, and then you can play around with that. But this is the idea, and see that we have a nice average, very uniform. That let's say we can say that this is okay. We have an average nice solution. So now that we did this one, you can export. Okay, so let me also, you can export that also. You have line chart, and let me put it here, and let me select just one. Okay, I'm putting everything. I just want this one. You can export also this one. So you go here, you select active view, go here, view data, save data, and then you select CFD, comma separated value. Give it a name. I know I will call it test. You can save the current time step, or you can say write all time steps. If you go like this, it will save everything. So let me show you. It will be a little bit time consuming. Okay, let's wait a little bit. So see that it's saving test 1, 2, 3 is the iteration that you have the time. So this one will save 350 files. And as you open this file, is the CFD file with all that information. Okay, in this case, I'm saving everything, but also you can select, you can specify what information in particular you want to save. So you can save just the coordinate of the points in that line, probably the arc length, and then the variable that you want to post-process. But you see that now having this data, now you can use an external software to visualize. So here, my computer now is crunching numbers. See that the fan is kicking in. So it's just rerunning, saving everything. So you can start to see that if you are doing this one for a very large mesh, probably can be a little bit time consuming. Okay, so let's wait. It will arrive to 350. Okay, and one thing that probably I haven't found an option to stop probably here. No, it doesn't stop. You need to wait until it ends. So that way it can be a good addition just to put a stop button somewhere. Okay. So I think this point is on 350, you have it all of them, and then you can post-process. So now we have another option here, pro location, which is this one here. So you can put this point, and then you can pro in this point, and you can put as many as you want, okay? So here we already have it, and to visualize this one, the idea, it is the same. Okay, let me go here. You split here, you go line chart, and you select this one. Okay, in this case you put the pro. We have a pro, okay, which is this one, this point here. Okay, and then here active the pro. But if you put a pro, you okay, let me split, then you can access the spreadsheet view. You can also do it for the line, and see that you have the value in this point. So see that you have all this information here, and here is where you can choose what data you want to put there. Okay, column visibility you can hide. Okay, so according to what you have there is what you are going to save in this CFD file. So as you press play, see that the information, it is updating. Okay, and then if you want to plot this one, you need to do plot selection over time. Okay, so you can select this point or cells, whatever. So this selection is general, so it's this one. Okay, extract selection. So in this case, select this one. Plot selection, plot selection over time. Sorry, it's this one. Okay, plot selection over time, apply to this one, and now you can access this one here and see that you have all the information at that point. Okay, so specifically there you're going to have, okay, so see that you can, in X you have time, okay, and then you can select, let's say I want just to see velocity and pressure, and see that you have those values there. Okay, so very straightforward. Okay, so hide that one, and then you press play, and you can see the animation there. Again, you can save the data, just gonna click there. Okay, let me stop. You can directly click here or click here. Okay, both are our equivalent, say data, and then you can save that information as we did previously. Okay, so this was how to plot that information, and I think you have an idea now how to do this post-processing. As you see, it's very powerful and can be very time consuming. So let's move to the last case, which is computing forces in Parafoam Paraview. Again, I recommend you to do it directly in OpenFOAM, but if for some reason you want to do it here, or if you forget to do it, you can also do it here. So I will show you how to do it. State 3, we have it here. Open. So we remember the forces, the total forces is the composition or the contributions, the pressure forces, and the wall shear stresses forces. You can compute wall shear stresses here, but it's very time consuming. Okay, you need to compute the derivative of the walls, then multiply by the viscosity, summation. So it's time consuming, so do it in OpenFOAM. Okay, I'm not going to show you, but have in mind that you can do it with no problem. So see here that now here we computed drag and lift. So you press play, okay, see that the animation, drag and lift, you have it here, very cool, very nice. Okay, so then we are going to compare with OpenFOAM. You will see that solution is the same, there is no problem. Also see that what you see here, okay, you see that the quality is not very nice, okay, you are missing points here, but this depends of the frequency, how you are saving the solution. Okay, so that's the problem. That's you want to compute a good signal here, you need to save a lot of time step, and that takes space, and then post-processing is heavier again. So that's why I recommend you just to do it directly in OpenFOAM. So let's see the steps to do here. So we go here, because this is require a few additional steps. Let me start to hide things here. So we start from here, annotate time, extract block. So in this extract block, we want to compute forces at the walls. So you need to extract the walls. Here we have just the cylinder, one body, extract that cylinder, and now we need to use pressure, okay, here to compute that one, and also wall shear stresses. Okay, so as you take pressure, let's visualize just pressure. Okay, we go here and see the next step here that we have. We use this one, we apply extract surface. This is just to convert the surface from the format, okay, that we have it. So this was the Exodus, I don't recall, but sometimes it's required, sometimes not required. In this case, we need it. So we put extract surface. So this is just a conversion, okay, of the type of surface. So this is nothing that strange. Okay, so see that you have it there, and it's extract to the boundary. Okay, so it's pretty much the same. Okay, so now you put it there, and now you can use the filter. Remember, generate surface normals. So you put it here, and when you use this filter, okay, again you have it here, you are computing the normals, okay, to the surface. So remember that lift forces, you will need to compute normals here. So you decompose pressure in those normals. So see, in this case, when you generate normals, you are smoothing the data here, and then generate normals, they are smooth. Okay, so that is the previous effect in the airplane case. We didn't see, but here you see clearly that it has this effect of smoothing data. Okay, so you put it there, and then if you want to see the normals, you can put the glyph. And attention, when you put the glyph here, you need to use orientation. You have many, now you have normals. So you put velocity, you will have velocity orientation, but as you put normals, you have normals orientations at the nose. And also be careful that in this case, the orientation of normal, you can change that. Okay, so you can, okay, well, you have it here. Okay, so you can use it by default is like this. So if you don't want the normals like this, you can just put it like this. So always have this in mind, because depending of this, you will need to multiply by -1 now when you sum the forces. Okay, just the orientation. Okay, so you have these normals. So what we're going to do is multiply pressure and wall shear stresses by the normals to get the decomposition of the pressure, vertical, horizontal axis, and saying wall shear stresses. So see that we have this, and now we add a calculator to this one. Okay, so as you look at this calculator, now we compute lift. How do we compute lift? Is pressure times normals in y. Okay, so okay, lift. Okay, we will need to decompose that one. We can access, but okay, you have the decomposition of that one will be the the dot product of that one, and you will get only the normal contribution. Okay, so see that this is actually the force distribution on the cylinder. Okay, so we have the force distribution here. So here, see that this is what I was telling you, that in, okay, now we're, well, it also depends on the vortex shading. Okay, but see that here we have here positive and here negative. So maybe we will need to multiply by -1, because here will be positive, negative. Okay, so be careful with your orientation, but it doesn't matter, it's just a sign. Okay, you get the idea. So you compute the force and see that we're adding wall shear stresses, but if you want, you don't add wall shear stresses here. These are the wall shear stresses coming from OpenFOAM. Okay, you can compute it here as well, but it requires some operation. So you can compute it like this, or you can put wall shear stresses, okay, in the same component. The contribution for lift usually is not much. For drag, yes, it's important to add it. So now you apply a second calculator here, and in this one, what we compute the drag force. And see that in this case, we have drag, so your component, your contribution here. And see that here, now we multiply by -1 to get the right side. In this case, you will see it later. So see here that we have negative drag here and here, which is not okay, it should be positive, okay? But just this is just a sign, a matter of a sign, okay? So well, then that after you do this one, see that we have this new filter, integrate variable. So as you go here, you can do integrals here. So the integral of the lift and drag over the surface will give you the total lift and drag. So this is the distribution, node by node or cell by cell. Now you integrate and you have that value, okay? So how do you see this one? Because this is a single value, okay? So this is a worksheet. And as you go here, see that you go spreadsheet view, and then here you have it. Okay, singular quantity, lift and drag. These are your integrals. Okay, you hide it, and so you have your two integrals here. And as you compare this with what is coming from OpenFOAM, the mean value, you will see that it's pretty much the same value. Then we can do more cool things. So here we have an extract selection. Okay, so I apply extract selection to this one. We're selecting this one, okay? So see that extract this selection, okay? So you select this one, extract this selection, and then we can, let me split here, and we can do a line chart view. Oops. Okay, line chart view of what? Of this one, plot over time. So it's computing everything. And see that we're computing all the quantities. So see that you need to extract selection this one. If you apply the filter directed to this one, it won't work. So extract this selection, the data, all this data becomes available. And now that you have extracted, and well, you see that you need to select here, copy active. Okay, so be careful, you need to enable, and then that you have it, you copy, it will plot over selection. This selection over time, you have it here. Okay, and now you have that. So you select there, and here you can choose what to plot. So as you go here, you have lift, and see that this is the lift signal. Okay, so if you press play, your lift. And what I was telling you here is that this one, you need to be careful of that sign. Sometimes you need to multiply by -1. In this case also you need, okay, so -1, and see that you are only changing now the orientation here, so it's nothing changed. So for instance, let me go here and let me choose drag. Okay, let's plot both. Okay, so drag and lift. Okay, so you have both signals. So as you go here back, see that here I multiply -1. So this is just reference system. So as I erase that -1, see that your drag now will be negative. Okay, it's nothing. It's not a big deal, just the sign, okay? And see that we're adding the X component of the wall shear stress. So this one you need to multiply by normals. Already from OpenFOAM is coming, right? But as you have the magnitude, then you will need to multiply magnitude by the orientation of the normals. So now that you have this, you can go like this, select this one, save data, you can save your data. Okay, so here, hey, let me press play and see that. Very cool, very nice. Okay, so here already in the folder, you will find in data, this is the data extracted. So it's LD Paraview, and see that we have all the signal, everything from here. Okay, so see that here you can choose what columns to plot everything. So here you should have lift and drag forces, and the last one is time, and then you can compare with what is coming from Parafoam. Okay, so let's do something. So now that we have this one, I hope you get the idea. As you see, there is a lot to do here. Things can be really complicated. So let me erase all this one. So let's do some plotting. So in data, you go there, and we can, no, let me go here and let me open new plot. So there in new plot, okay, you can plot. See, here you have this README file. So here you have some instructions to do the plotting. So for instance, you want to plot this signal. So see here that in new plot, we're manipulating the file, the output, because we have this, comma that new plot will give you problems. Okay, so you try to plot with this comma, it will complain. So what we do is you set search for this comma, substitute with a blank space, do it globally. So we're doing this within new plot. So we are not modifying the files, just on the fly, and then plot this data. Okay, so let me show you here. So you're plotting the output here. So let me show you now. If you erase this command here, it will give you a problem with the data. Okay, see. So put that one, erase the comma, and the same with the parentheses, those below the parentheses, that it will give you problems. Okay, so for instance, here you have the command. For instance, the data coming from OpenFOAM for forces, it has the parentheses. So see here that, look, the brackets is for the what you want to look, and and you look for parentheses, substitute with a blank space, and then plot the data. So to plot the current data, okay, this is the comparison. Sorry. So let me go here and see the comparison. So see that we have the two signals. Okay, let me zoom here. So this CD is the one coming from OpenFOAM, and this is the one computed here. Okay, so and see that pretty much the same. The problem is that you have this, okay, here, because it's the sampling frequency. By the way, here also you will see that I'm multiplying by -1. I know the leaf, I think you see my -1, okay, because when I save it, I forget my reference system. So now let's multiply. So this was, okay, we have the drag signal. Okay, nice. See here, boom, the on-second stability, and you have it there. And then if you go to leave, the comparison of both signals. Okay, so see that pretty much the same, but you have this error, but this is just the saving frequency. And just to show you that here, you erase this minus, is what I forgot when doing the post processing to multiply by -1. See that pretty much the same, but it's kind of out of phase, because okay, you need to multiply, you have different signals. Okay, so if you multiply by -1, you solve the problem. Okay, but again, this is just a sign problem. Okay, I think we have done everything here. Okay, I showed you also how to do with new plot, that erase those parentheses and commas values that might give you problems. Okay, so I think at this point we're done. I hope you enjoy it. So as you see, small cases take some time to do in Parafoam. So I guess at this point we have all the tools to do post-processing, meshing. We understand what case structure. So next videos we start to move into finite volume method, and there I'm going to give you my recipe and some brief theory behind the finite volume method, a general theory, in CFD. Okay, thank you very much, and see you in the next videos, next model. And I hope you are enjoying and having a blast. Bye, and see you.